Welcome to lecture 21 of the course Introduction to Data Science. The topic of today is big data. In other words, how can we deal with large amounts of data and give answers immediately. Let's put this topic into the bigger perspective that I've also used before to position things. Then if we look at the lectures that we have seen so far, most of these lectures were focusing on the analysis part. We have seen a wide range of supervised and unsupervised learning techniques that all aim to turn the data that is available into all kinds of analysis results, to automatically make decisions or to make certain diagnostics that help us to improve systems and processes. In the last two lectures, we focused on the effect part. So what kind of effects does data science have on people, organizations, and society? And we zoomed in, for example, into problems related to privacy. So we looked at techniques how we can protect confidentiality. And we looked at issues like fairness. So sometimes if our data is biased, then also the models that we learn based on this data will have the same biases. So that was the effect size. In the beginning, we also talked a bit about the infrastructure, but not in any detail. That's something that we will do today. Of course, we have seen in many lectures, let's say, things related to pre-processing the data to prepare it for analysis. Today we look more at the, let's say, things like scalability and dealing with limitations in terms of computing power and time and storage. So this is an outline. First, a big overview of let's say, the types of issues that we have. Then I will describe big data in terms of the four V's. Then we talk broadly about possible infrastructures. So you will see things like Hadoop and Spark, but not in a lot of detail, because it doesn't make a lot of sense to talk about this in theory. This is something that you can do yourself in the two instructions devoted to this. Then we become a bit more technical. I will explain you the MapReduce approach that helps us to decompose a bigger computation into many small computations that can be handled in a distributed manner. Then we talk about streaming, and to be concrete, I explain to you a variant of the k-means algorithm, which have been tailored towards dealing with streaming data. In that context, we will also talk about concept drift. So that's the program, and let's start by talking about big data, where it comes from, and what has changed. So if you look at the classical problem of data science, was often this, that we had too little data in order to draw reliable conclusions. If we were taking, for example, a sample from a bigger data set manually, then the problem was always that based on this small sample, we had to figure out what we could now say about the bigger data set. If you look at how data is collected today, we no longer need to take a sample. We can simply take all the data, and that leads to very different problems. Also, we have all kinds of new data sources that allow us to get access to data that we would not be able to see in the past. So where does it come from? I think that's obvious: internet, social media, but also, for example, in healthcare and production, large amounts of data are being produced. Think also about self-driving cars, e-government, also smart homes. If at home you have Alexa and automated lighting systems, etc., then you realize that around you lots of devices are connected to the internet. Just to illustrate, let's say, the volume, here you can see in this infographic what is happening in the internet a minute. And here you can see, I don't know, how many text messages there are being sent, how many hours of video are being watched, etc., etc. The number of tweets per minute. This is all amazing that this is possible. That is possible, and also what is responsible for generating this is, of course, our increased ability to compute and to process data. I think a very nice illustration of this is that here you see a picture of the Cray supercomputer, the Cray 2 supercomputer, which was the fastest computer in the mid-80s, that has a processing speed of 1,9 gigaflops. If we look at an iWatch today, so an Apple smartwatch like the one that I'm wearing, that has a computing capacity that exceeds, let's say, the Cray supercomputer many, many times. And the Cray supercomputer would require a separate building, and now it fits on my wrist. So this is showing where the data comes from and how much it is. What's also changing is that we live in a so-called platform economy, where there are all kinds of platforms that are used to provide us with various services and products. So there are the transaction platforms. So these are, let's say, Amazon, Alibaba, Uber, etc., that try to match supply and demand. So for example, if you look at a company like Uber, there are people that have cars, and there are people that want to move from point A to B, and they find each other. If you look at something like Amazon, we have people that want to sell something, we have people that want to buy something, and the platform brings them together. There are also technology platforms, like, for example, the app stores of Google and Apple, that provide an infrastructure, and people can build products on top of this. And then there are, let's say, more domain-specific platforms. So, for example, a few years ago, I made a Coursera online course on process mining. So Coursera is like a platform that provides, let's say, electronic courses to people. And that, of course, that's one example. There are many more. Also, if we look in our homes, there is, for example, Amazon Alexa, Apple HomeKit, etc., Philips Hue, all kinds of platforms that exist in our homes and where things are built on top of. So there are these platforms, and what is interesting about these platforms, also possibly a negative side effect, is that the winner takes it all. So the winner, if a party has a certain scale, then it's very difficult for other parties to compete, and that party will also take your data. So why is this different from the situation before? It is different from the situation before because there is the so-called network effect. So, for example, if you would have a Facebook and Facebook would just have, let's say, 10 people on it, it would have very little value. The value is Facebook because many people that are interested in something like that has a Facebook page, and the more people join, the more valuable the network gets. The same applies to Twitter and all kinds of other things. Also, the marginal costs are very low, so it's very expensive to build up a computing infrastructure globally that is able to handle, let's say, these large amounts of data. But then adding a new customer, the costs of that are close to zero. So it is not that if Amazon is now selling twice as many products per day, that suddenly the costs would be twice as high. That's of course not the case. So the marginal costs are very, very low, and data is being collected, and that gives these platform companies all kinds of opportunities that other people do not have. So these platforms and these infrastructures, of course, provide excellent opportunities for data science technologies. One interesting phenomenon is that we see, let's say, an increasing alignment between the physical world and the world that exists in information systems. If you look at the classical store, what was in the information system and what was happening in reality did not necessarily need to be exactly the same. If you look at a company like Amazon, of course, what is in the information system is the reality. Also think, for example, about, I don't know, flight tickets. Probably many of you cannot imagine that, but you used to have a paper ticket. And the fact that you had that paper ticket provided you with access to a particular flight. Today you can print it yourself, or it's on your iPhone, but it's no longer that physical document is important. It is more an electronic code that's being used, allowing you to have access to a particular flight. So the alignment between reality and the data-driven world has become very, very tight, and that provides all kinds of opportunities to what is called here removing operational friction, making things much more effective, and for example also comparing different strategies, A/B testing, to see what is best. So there are lots of opportunities, and these have an incredible value, and I'm just showing you the classical examples. So if you're using Amazon and you log into the Amazon website, Amazon of course knows exactly what you have bought before, so it will try to push products to you where they think that you are likely to buy them, that you want to buy them. It is sending targeted emails based on your history, and these targeted emails are apparently very, very effective. Another example would be Netflix. Netflix, based on what you've seen in the past, it tries to derive what is your taste, and it is pushing certain movies and certain series to you where Netflix thinks, okay, this person is going to like this. As I said, this is effective. So McKinsey estimates that 35% of all purchases done on Amazon are generated through these recommendations. And when it comes to Netflix, 75% of what people watch is based on the recommendations that Netflix is providing. So this shows that this is big business, and that these things have an important value for these companies. So what we see is when we talk about big data and we talk about the capability of doing this, on the one hand we have the technological advances allowing us to deal with large amounts of data. On the other side we have, let's say, increasing requirements and expectations. For example, when people today order something from Amazon, they expect that item which they buy, they expect that item to be there tomorrow. So that is only possible because Amazon is using predictive techniques to kind of predict how they should move the goods already in order for you to get the product in time. So what sounds very, let's say, perhaps a bit odd is that in many cases Amazon is already moving products towards you before you have even ordered them. And this shows the value and the capabilities of big data. So big data is often described by 4 V's. There are even people that have come up with 8 different V's. Here I will focus on the classical 4 V's, where the V stand for volume, variety, velocity, and veracity. And I will explain these 4 V's. As I said, there are more in a bit more detail. But I think you already can guess what I mean. So volume simply refers to the size of data. So we used to talk about kilobytes and megabytes, and now we are talking about exabytes and zettabytes. And this is each time we change the word, there is again a factor 1,000 in terms of capabilities that has been added. So this is describing the growth of the digital universe, as it is called, with amazing amounts of data. This is a similar diagram. I think many of you have seen such diagrams which show the exponential growth of data. And this is not, let's say, hypothetical. This is simply things that you can measure and that you can see happening. So earlier we talked about Moore's law, and you can see here Moore's law in action in all different dimensions. We've seen, when we were talking about big data, we have seen what is happening in an internet minute. But for example, just to give one example, think about a company like Spotify. So Spotify has 320 million active users, so users that have logged on and used Spotify in the last month. There are 60 million songs, tracks. So if you think about a table that would only record how many times has a particular person listened to a particular track, then we have a table with these dimensions. So if you look at these numbers, then you can see, yeah, this doesn't fit in your ordinary laptop. You need to have a special infrastructure for that. And this is the topic that we will talk about today. So the key question of talking about volume is how to instantly collect, store, and process all of such data in an economic and reliable manner. So that was the first V. The second V is a bit different. It talks about the variety. And so we have different types of data. We may have image data, location data, network data, time series data, text data, and structured data. So in this course we have been mostly focusing on structured data, but many of the principles can be applied also to these other forms of data. We talked about, for example, sequence mining and process mining, where this temporal dimension is clear. We also had 2 lectures devoted to text mining. Also, if we go to images, etc., we will see many of the same ideas. But data is typically heterogeneous. We have different types of data, and there are 4 types of variety that we see here. First, there is structural variety. So we may represent, for example, a timestamp in different ways. So there are different formats, different types of models. So how do we store, how do we exchange such data? So that's structural variety. Then there is media variety. So for example, where is the data stored? Is it stored on a hard disk? Is it stored somewhere in the cloud? Then there is semantic variety. We spoke about that before. It's very important to capture the meaning of data, and there can be different representations of exactly the same IDs. And sometimes things are represented exactly the same, but they mean completely different things. And then there is variety in the availability. Some data is updated real time. Other types of data we only see in batches. So for example, if we look at sales data, it could be that some sales data are updated, let's say, instantly, real time. The moment that somebody buys something, it is immediately recorded and visible. For other products, it may be that this is updated only once per week. So we have these forms of variety, and just to look at the different forms of data that you find, for example, in social media. So here you see a LinkedIn page that has structured data. that we can interpret, that we know what it means. That can be videos shared through LinkedIn. Of course, there's lots of unstructured text, people typing certain messages, and there are all kinds of pictures everywhere. Also, if we go to Twitter, it is, let's say, very much the same. So we have structured data, so for example, how many followers one has, how many people liked a particular tweet. There is unstructured textual data, pictures, videos, etc. So that's for the variety part. Next is the velocity part. Velocity is related to speed. So data is coming in at such a high speed that you do not have the time to store it and to analyze the data later. You need to handle it immediately. So velocity refers to the speed at which the data is being generated. Then the question is, what can you store? In many applications, the speed of data is so high that you cannot store the data in the form that it is generated. You can, for example, just store aggregate information, and you need to analyze it. And because you cannot store it, means that you cannot go back in time. So just to give an example, you can look at like the engine of a plane, which is generating so much data that there is no way that you could store that data. So that data is being generated and analyzed immediately, and only let's say statistics computed over the data are being stored. Here you can see another example. For example, at the Alibaba store, and then you can look at what are the peak volumes. And Alibaba, like during, let's say the kind of Chinese Black Friday, needs to handle 600,000 deals per second. And that leads to an incredible amount of database operations behind it. So how to handle this type of data? So it's streaming. So as this cartoon shows, there is no time to carefully store it and to think about it later. As we need to process data immediately while having a strict memory constraint. We will talk about the topic of streaming data in a lot of detail in the last part of this lecture. Okay, so we have seen 3 V's. Now we go to the last of the 4 V's, that is veracity. And veracity refers to the uncertainty of data. So it's also called data in doubt. So on the one hand, we have these large amounts of data, but often we do not know enough about the quality of the data, and sometimes data is being recorded where we do not know the exact context. So here are all kinds of, let's say, sources of, let's say, possible uncertainty. And if we are handling big data, we need to have an idea of what we can conclude from this data. So an example would be, this is an electronic shaving device. It is giving you advice on how to shave, let's say, better. So the shaving device is connected to the internet and it is trying to give recommendations. Also, the company that sells these devices is analyzing what kind of beard people have. Right? So this is all very sophisticated, but it's all based on the assumption that the same person, the person that bought the shaving device, is actually using it. But in my case, for example, many of my old shaving devices get passed on to my sons, which may lead to, I don't know, the conclusion that the skin, that I got a much better skin than I used to have before. So this is show, let's say, the 4th V, this uncertainty in data. Also in the time where we live, where we have to deal with Alexas and Siris and other types of things, It is showing how often, let's say, neural networks are trying to interpret the situation and may make completely wrong conclusions. So we have lots of data, but we need to interpret them carefully, because there may be all kinds of misleading things in the data that we need to look in much more detail. So after dealing with the 4 V's, we are now going to focus mostly on the first V and the third V. So things related to the volume and things related to streaming. So if we look at big data infrastructures that look like this, they are intended to be able to deal with these massive amounts of data. And the problem is very easy. If you have hundreds of petabytes of data, you cannot store that on your laptop with 4 terabytes of storage. You need to have many, many computers to be able to store such data. Also, if we look at the computing power to process, to do complex operations on hundreds of petabytes of data, you cannot do that on a single CPU. You need to have thousands or hundreds of thousands CPUs to do that concurrently. So the only way to deal with this is not to have one faster CPU and one faster, bigger hard disk. No, we need to deal with that using concurrency. So we need to distribute the computation. So Google is a prime example of an organization that saw that very easily, very early, and this explains their success, rather than trying to use specialized, let's say, supercomputers, specialized hardware. They went for something different. They went for, let's say, cheap commodity hardware, nothing special, but they do the scaling by doing this in parallel at an incredible scale, and also building systems that are redundant. So by having many concurrent cheap commodity hardware, when one system fails, that is not so much a problem, and one can scale very easily. So that's the challenge. So concurrency is one important notion. Another important notion is that the distances in computing are very important. So if you need to move data to a particular node and then do a computation, then things are taking a long time. So here you see some times, how long it takes to access certain data. Note that these figures are from a couple of years ago, but the IDs are exactly the same. So everything has become faster, but relatively these things are still very much similar. So of course, if you want to do a computation, you need to use the CPU. Then you have very quick access to the cache of the CPU. You are relatively fast when you need to go to main memory. It takes much longer if you need to go to a hard disk, specifically if it is a classical hard disk, so it's not a solid state drive. Just to illustrate that these times are very different, I use the metaphor of getting a coffee. So if we look at the time to when the CPU needs a particular let's say data item, and it is in the cache, then one can think of that as, okay, you're going to the kitchen to get a coffee. If that same data element is in main memory, you need to go further, but it's still okay. If it's in main memory, it is relatively fast. And compared to first going to the kitchen, that means that you need to go around the corner to Starbucks to get the coffee. So that is still okay. If you need to go to an SSD, which is much faster than a traditional hard drive, Then getting that cup of coffee, if we measure it in terms of distances, like kilometers in a relative sense, that would compare to flying to Milano to get the coffee. So this shows that you should keep the data that you need in main memory, otherwise it takes much more time. If it's in a classical hard drive, then it corresponds relatively to flying to Colombia, Ethiopia, and Kenya, process the beans in Amsterdam, and then fly to Rome to get the coffee. So that is showing, let's say, the innovations. So to summarize, we see three important trends. We want to keep more data in memory to avoid the coffee problem that I just explained. Then data is too large and we cannot do it sequentially, so we need to distribute it. And we are using commodity hardware to do that, where we scale by adding more and more hardware, also in a redundant way, that if one node fails, not the whole computation fails. To use this distribution, we need programming models like MapReduce that I will explain in this lecture. Finally, we have the problem of streaming. That means that you need to do new types of computation where you can no longer, let's say, first store the data and to analyze it. You need to analyze it on the spot. In the last part of this lecture, I will explain you a streaming k-means algorithm where we are not actually storing the data, but processing it immediately in batches. So, if we look at infrastructures, and I will be relatively brief here, we can look at a big data platform like Hadoop. And Hadoop is, let's say, one of many examples. It's already a bit classical. I will not talk specifically about Hadoop, but I will try to focus on the principles that these infrastructures are using. So this is showing a bit of a time a picture, and also showing the increasing complexity of these infrastructures. So in this lecture I will focus a bit on the classics, although let's say later many things have been added to it. The MapReduce algorithm and the file systems that are used to handle large amounts of data in a redundant and reliable way. So this is describing the Apache Hadoop ecosystem. As I said, I will not talk about this in much detail. During the instructions, you will install Hadoop yourself, and you will play with the Hadoop system so that you have some ideas. But the goal of this lecture is not to say things that are very, let's say, system specific. Because this is the landscape, it is very confusing because all of the different vendors and systems that are there, and it is changing all the time. So there is no point in this lecture trying to tell a lot about this. It is something that is much better to be experienced hands-on. Instead, I will focus on the foundational principles that are a bit independent of these vendors and these different systems that are available. So a core element of being able to handle large amounts of data is, of course, that we have a distributed file system. So the idea is that we do not try to store the data on one hard disk. No, we have many nodes in our network that are all able to store data and to process data. So the distributed file system does that. And if we want to write a file into this distributed file system, we cut the file into different parts. So for example, here I'm looking at one big file which is split into 5 blocks. And we put these blocks on different nodes, and we do that redundantly. That is shown here in this diagram. So if we write this file to the distributed file system, We split it into, for example, 5 different parts, and we do not put all of these 5 parts on the same node, because if we would like to do a computation based on this file, that would mean that one processor would need to do the whole processing of this. So we put it into different parts, and we also replicate it a couple of times. And because of the distribution and the replication, we achieve 2 things. We achieve that we can do computations concurrently, because data is residing on different nodes, and we have redundancy. So for example, if this node would crash, we still have a copy of 5 and a copy of 2 at other locations. So we want to have concurrency, scalability, and fault tolerance, and we achieve that by cutting our data into parts and distributing it in a redundant way. So the Hadoop distributed file system looks then as follows. So we have the data nodes where we actually store the data, and we have the name node that you should think of as a kind of phone book that tells us where the data is located. So a name node is the heart of the system, and it keeps track of where the data in the system is. And note that a particular block of data will typically reside on different locations. So here this is visualized a bit. So we had this one file that is cut up into 3 blocks, and this is showing the location where these blocks are located. There is another file consisting of 2 parts, and also it's indicating where it is. So if we want to do a computation on this file, for the A part we can go to node 1, node 2, or node 4. For the B part we can go to node 2, 1, 2, and 3, etc. So in principle, if we do a computation based on A, B, and C, we could have node 1 could take care of doing the computation over the A part, node 2 could take care of doing the computation over the B part, and node 5, for example, could take care of the computation over the C part. So this could be handled concurrently. So the data node is the part where so the name node is the phone book, the data node is where the data actually resides. So we achieve fault tolerance because we duplicate information. So if one node crashes, that is not a drama because it still exists at 2 or 3 other locations. And we get scalability because the same data is on multiple nodes. And if we have thousands of nodes, we could potentially let them all work concurrently. So that's the basic idea that I just indicated, and we can redistribute the data based on let's say, our requirements. And also, if data is growing in size, we just add more hardware to facilitate that, without making the system slower and slower and slower. So this is a bit redundant, so we achieve parallelism because the same data is at multiple nodes, and it is fault tolerant because if something crashes, there is not a problem because it still resides at other locations. As I mentioned, one of the key ideas in the beginning years of Google was to use cheap commodity hardware and expect that hardware to fail, rather than having very expensive, sophisticated hardware where we expect that the hardware is always going to work. And that was a key differentiator, probably leading to the success of Google that we see today, and many of the other companies in this space. So just to show you what is happening to such a compute cluster, these are some numbers given by Jeff Dean from Google. This is what is happening to a first year of a new cluster. You can see that all kinds of problems occur. but because of the redundancy that I mentioned, this is not a major problem. Of course, what is a major problem that we see today is the energy consumption. So we are using this concurrent hardware, but of course all of this hardware is consuming energy. So that is why often these data centers are located at locations where it is possible to get energy cheaply, or where we can use, let's say, green energy. So we can see that this is becoming a major cost factor. And if we look at it, in the beginning, the energy consumed by ICT was relatively limited compared to anything else, but today it is a major factor. So just look inside such a data center and you can see that energy is one of the bigger concerns here. So apart from the energy question, of course, the key question is if we want to do certain data science tasks, how can we exploit this concurrency? And of course, we use a divide and conquer approach, where if we need to do a huge computation, which potentially would take, I don't know, years to compute, we try to break it down into many smaller computations that we can run on, for example, 1,000 different machines, as you see here in the background. Okay, so that was, let's say, the more informal part. Let's now take a look at the classic, let's say, in distributing computation, and that is the MapReduce programming model. And so you can think of MapReduce as an approach, as a way to code certain analysis tasks in such a way that you can run it on this highly concurrent hardware. And MapReduce originates from people within Google, but the IDEs are not, let's say, that original. And so the basic idea is to find a generic way of decomposing a big computation into many small computations that you can run concurrently. So the main idea is illustrated in this slide. So we want to do a certain computation, and we try to split the computation into two parts, and both of the parts can be done concurrently. That is the map part and the reduce part. And the Hadoop infrastructure, or whatever infrastructure that is being used, is taking care of the wiring between the output of the map step and the input of the reduce step. So this is like a high-level picture. Here I'm trying to be a bit more precise, and probably this only becomes clear when I show an example later. So we have different key domains. Here I'm using K1 and K2. These are keys. And we have value domains. So we are looking at key value pairs. Then we have a map function that is taking as input a key from the key domain K1 and a value from the value domain V1. And the map function is something that you need to program yourself, that is transforming this into something else that looks as follows, where we have a sequence of pairs composed of, let's say, a key from the K2 key domain and a value V2 from the V2 domain. Then we have the reduce step that is taking this as input. So we take a key from the K2 key domain and a sequence of values from the V2 domain, and we generate a sequence of values from the V3 domain. And now what you see is that the output of the map is a is a sequence of K2 times V2, and the input of reduce is K2 times a sequence of V2. And the infrastructure, so that's the main task of the infrastructure, is to convert this into this in a way that is super efficient. And that's what was called the shuffle step in the slide before. Okay, this sounds very abstract. It's best to just show it using an example, and also during the instructions you will play with this yourself using a concrete system. So the map step has this signature. So K1 times V1 is producing a sequence of K2 times V2 values. So here, if we look at this example, this is counting words. We have, for example, 4 computing nodes, and at each of these 4 computing nodes, for every text document, we apply this function. So here we are at a particular node, and K1 is the identity of this document, and V1 is the content of this document. And what comes out is a sequence of key value pairs, and the key value pairs here are words and the frequency of a particular word. So that is listed here so that you can make the mapping. So K1 is the identity of a particular document. V1 is, so elements of V1 is a particular document text. So K1 is the identity, V1 is the content of the document. And then there is a map function that is converting this V1 into pairs of K1 and V2. K2 are words, V2 are frequencies. And in this simplistic example, the V2 value is always 1, because that is what I need here. So we have a map function that we need to describe ourselves, that is mapping a text document into a sequence of words that are appearing in this document, and that are such a key value pair. This can be done concurrent, so at all of the nodes we have a large collection of documents, and for every document we are doing this step. So we can distribute this, of course, if you have millions of text, you can do this, let's say, very much in a distributed manner. Now the problem is that all of these key value pairs, so of a word and its frequency, reside at all the different nodes that we have. And then we have the shuffle step, that the infrastructure is taking care of that. That is, let's say, combining the elements that have the same K2 key and putting them on a dedicated node. And so now we have a node for every K2 key, and the infrastructure is doing this automatically. And so this grade comma 1 is being converted to this. So the output of the shuffle step is that we now have data of the form K2 times a sequence of values of type V2, and what we generate is a sequence of values of type V3. So if we look at this example again, then K2 is still the set of all possible words. V2 is the set of all possible frequencies. In this example it always happens to be 1, but we could optimize for this. V3 is the set of possible frequencies. That is the numbers that you see here. You may wonder, it also says action here, but in this, let's say, classical setting of MapReduce, there is an implicit key here, so you can, but it's the same one, so we don't need to repeat that as information. The K2 that is added here is the same one as the K2 that is added here. So here, this action, comma 1, 1, Here the reduce step is taking the sum of these numbers and we get action, 2. What's important to note is that this K2 key only appears at this particular node. And the shuffle step made that clear. This example is a bit, let's say, simplistic and very simple. What you have seen is all the time that V2 was always equal to 1. But if I go back to the original setting that we had here, if within 1, so for example the word data is appearing twice here, we could optimize over this, that if we have such a document that we could write data, 2. And so we could already aggregate things here at this stage, and then we would not just have once, then we would have the frequency per document. Then the V2 values would not be just once, as we see here, but in the end this operation would be the same, because we are simply taking the sum over all the numbers that we have seen here. So for example, fun, we have 5 times 1, and this would then this could then be like a sequence 3, 2, 2, 1 or something like that. So what I just mentioned is that this can be generalized. What I also said is that the K2 key is kind of implicit in this basic algorithm, because it's exactly the same. So if I visualize it, this action key here is the same as the key here. In the more general format, we again have a mapping where we are mapping K2 times V2, a sequence of that, to a sequence of K3 times V3 values. In our example, this K3 was the same as the K2, right? This is just a generalization of what we have seen before. So this shows the overall way. This is our input, this is our output, and we are able to count the frequency of words in millions of text in a concurrent way. I'm also going to show another example using process discovery from the lectures on process mining as an example. Here, based on event data, we would like to learn a process model. And assume now that we have an event log that contains, I don't know, billions of events. And we cannot run this on a single laptop. We need to use, let's say, like a concurrent infrastructure to create such a process model. How can we do that? So assume that the data, the event data, is already distributed over multiple nodes, and we are using MapReduce. So what I'm showing you in this diagram is that, like it looks very similar to the previous example, but now we are not looking at a text, but we have partitioned our huge event log with billions and billions of events and cases. We have split that over multiple nodes. So every row here corresponds to a particular case, a particular process instance. And every trace is converted into a pair of activities where we have a special symbol for start and a special symbol for end. So this start symbol here is indicated that is happening once. Then we look at A is followed by B, that is here, etc., etc. So here we are basically encoding in this part of the bigger event log. When we see one activity followed by another activity, we write one such a pair. And again here, just like in the counting the words, is our V2 data set only has ones in them. But again, we could optimize this, and we could already aggregate at this stage. So for example, we could combine these start A pairs by one start A pair, comma 4. This is happening 4 times. So this is the map step. Then we go to the reduce step. So all of these pairs are using the shuffle operator are all, let's say, combined. Every pair of activities is residing on one of these, let's say, reduce nodes. And here we basically aggregate the number of times. So based on this, we now know that A is followed by B happened A times in our entire data set. So the map part can be done concurrent and the reduce part can be done concurrent. So this is just following the programming model that we just did and using such, let's say, directly follows relationships with frequencies can be used to construct a directly follows graph, and the directly follows graph can be used to create, for example, a BPMN model or whatever process modeling notation you like. What you should learn from this is that using MapReduce, we can do process discovery at the scale of Google. So the more hardware you have, the larger the data sets are that you can cope with. So this is very efficient and shows scalability. So MapReduce is one of the elements that you should understand. It is one example of making a computation concurrent. We have seen this before. So we have seen that getting data from the cache is like getting a coffee from the kitchen. Getting data from your hard disk is the same as flying to Colombia, Ethiopia, Kenya, Amsterdam, and Rome, and only then have your coffee. So we see the trend that more and more data is kept into memory and is not stored on disk because this is slowing things incredibly. So if we look at the classical Hadoop infrastructure, there was still the idea that data would be stored on a disk or like this cheap commodity hardware. But if the steps in between different steps, we need to store the data on such a hard disk, then computation goes incredibly slow. And it's like flying to Colombia for a cup of coffee. At the same time, we see that memory costs are going down. Of course, the cost of a hard disk is going down, but also the cost of, let's say, main memory is going down. So the cost of main memory today is comparable to the cost of per, let's say, megabyte is comparable to the cost of storage on a hard disk a few years ago. So this explains why we see a trend where hard disks are replaced by, let's say, main memory to make things much faster. And the Spark infrastructure is basically responsible for this transition. There are many competing paradigms and you can mix these things in various ways, but that's the main idea. And if things can be kept in memory, then of course that is much faster. And so here you see an example computation where blue is Hadoop, where the speed is much slower because intermediate results are stored on a hard disk rather than kept in main memory like it is done in Spark. This is of course not a completely fair comparison that shows these developments that I explained in the beginning, how they are playing a role when we are computing over data. A problem that I mentioned, it was the third V of the 4 V's of big data, is streaming data. The velocity of data is increasing in such a way that we cannot always handle and cope with the number of requests that we are getting. So the x-axis is showing when, at what point in time an event happens, and we need to do a computation or we need to provide a response. And the skew is kind of showing what is the delay So something happened at a particular point in time. When was the corresponding response? And if this gets delayed, then that is of course problematic. So the bigger this gap between this diagonal and the actual time, the bigger the delay. The problem is that because we have limited storage, we need to be able to handle the situation that we simply cannot process the data. We should then not crash. We should still, let's say, have a graceful way of handling such problems. So this is talking about a situation where we have to deal with limited capacity. We cannot say if, okay, the bucket is filled with water representing data, and is overflowing, that we say, okay, now we stop. Now, if the bucket is overflowing, we continue to work, and of course, we will not be able to do an optimal, let's say, computation, but we start approximating. So we drop certain data in order to still produce results, even if they are not optimal. And there are many situations where we simply have so much data flowing in that we cannot store it. We need to throw it away. On the one hand, on the other hand, we try to use as much data as possible. So here you can see an example using, I don't know, cars that are monitored along a highway or something like that. There is a continuous stream of lots of data that is flowing in. And if there are too much cars coming at the same time, it may be that you're unable to process it. For sure, you cannot store everything. And if you want to do some type of analysis, you cannot go back to a car that was driving there 3 years ago, right? You don't have the time to do that, and you don't have the memory capabilities to actually store such large amounts of data. So in streaming, this is much more fluid. So you accept that you throw away and you forget about data, and you just try to handle the data in the best way possible. So what this diagram shows is that if you're dealing with streaming data, there are three main design decisions. The first is, again, distribution. So how do you distribute the data? There is a source that is generating the data, for example, a sensor. There are consumers of that data, and how do you connect both? Then the second problem is the data range. We need to look, okay, what is the data that we now consider for our computation? When do we drop data? When do we consider it to be irrelevant? And there are the operators that we use to process this data. And I will walk through these three design choices and elements step by step. So the first one is the data distribution. Suppose that I have a sensor that is generating lots of data, and I have multiple nodes that potentially want to do something with this data. Then if you are using unicast, you would, so this data source would send data to all of these systems. These systems would acknowledge the data, perhaps based on the type of data, you would send it to particular systems and not to other systems. And this is what is called unicast. So we have a one-to-one transmission. This may be a very bad idea because if one system is crashing, it could block the whole network, and you put the burden on the provider of data rather than on the consumer of data. So a better mechanism, rather than using unicast, is to use, let's say, a broadcast. So where you have middleware, just like the shuffle operator in MapReduce, which is making the connections in a sophisticated way. So the node that is publishing the data, for example, the sensor, which is emitting lots of events, This sensor just sends it to the middleware and doesn't have to care about it anymore. The middleware is doing a broadcast, one to many, and we have these nodes that potentially do something with the data that subscribe to particular topics. And this way, the middleware is taking care of the connections, and we are using publish subscribe rather than unicast. And this way we can decouple the production of data and the actual use of data. So that was design decision 1. Design decision 2 is what kind of data do we consider? There are different alternatives. So the first alternative is what is called the landmark data model. So we look at a particular point in time, and from that moment on we start to record all data and do not throw away any data until we set a new landmark, and then we start again from scratch. That's one model. We have to realize that we are dealing with capacity constraints, so we cannot keep the same landmark forever, because our memory will overflow because we cannot store all the data indefinitely. That's why we can also use the sliding window model. So there you're looking at a window in time, and you keep all the data that was produced in that particular time window. So the time window is moving gradually, and things, data points that are outside of this data window, they are simply forgotten. So what falls out of the sliding window is basically removed and no longer accessible. Then there is the damped window model. So with the sliding window model, we use data points when they are in the model, in the window. If they fall outside of the window, we basically forget them. In the damped window, we are basically using aggregate information. So we do not keep all the individual data points, but we store aggregates. Later I will talk about, let's say, the streaming k-means clustering technique, and there we see a parameter that is doing exactly this. So we are giving more attention to recent data, less attention to data that happened in the past, but in principle we do not forget anything because it is kept in aggregated form. In a minute I will show an example of that, and it will become clearer. The third element in designing such a stream is, let's say, the network that is actually processing the data. So we can think of the computation as a network where different operators act upon the data that comes in as a stream. And there we look at two types of operators that are stateless and operators that are stateful. So stateless operators, the only thing that they need is the input data, and it doesn't matter what has happened before. That's of course from a computational point of view, it has many advantages. But of course there are many operations that you cannot do in this way. There you need to use stateful operators that somehow keep track of things that have been before. So each time the operator is called, it has a particular state, and what it produces depends on the input and the state it is in. So if we look at stateless operators, that could, for example, be a filter. I don't know, throw away all the numbers above 100, or split the numbers into the numbers below 100 and the numbers above 100. We can do a conversion of the data, and if there is something like an XOR join, so different streams come in and we merge them into one stream. These are all stateless because what comes out only depends on what went in. Then there are the stateful operators. here there is a dependency between the state of a node, which is based on things that have happened in the past, and the input. So here the output depends on the state of the node and the input. And stateful operators may also be used to kind of combine two streams based on a specific predicate. And so these nodes have states, and that's why they are called stateful operators. Just to show an example, because I think that very nicely illustrates the problems that I've been talking about, is in the field of process mining. So we have a stream of events. Events are things that have happened at a particular point in time. And this stream is in principle infinite. So if we observe a system for an unlimited amount of time, we collect more and more and more data. So what we have is that we store these events in memory, but in memory we are using queues or windows. So we also drop things. We do not remember all the events forever. We start dropping events the moment that our memory is full. Based on this limited size memory, we can compute intermediate structures like the directly follows graph, and the directly follows graph can be used to, for example, compute a BPMN model or a PetriNet or whatever type of model you would like to have. So this is showing the problem that one of the key decisions is that we need to forget about things. This is visualized, let's say, very nicely in this diagram. So this was the stream, but every event corresponds to a case. And if we look at a process model is basically describing the life cycle from a case from beginning to end. So here we have the data that is still in memory. This is the data that will arrive in the future. And we need to forget about data. So if we use a simplistic memory management and we just drop the events that are the oldest in our memory, then we get the following problem. If we drop this A here, and this AC and this A, and we have forgotten about this, then we may think that the process can start with activity B. But if we would have stored all the events, if we would have been able to do so, we would see that the process never starts with B, it always starts with A. Also, that's on this side, we never know for sure when a case has ended. So here we have an F, and because F is often the last activity, we may think, okay, case 2 is now closed, but we cannot be sure that in the future something will arrive. So there are two problems. We do not know when we are done, and we need to drop things from memory that may lead to errors in our analysis. There is, of course, another issue, that is, if we talk about a process model of a process, and the process itself is changing over time. So, for example, the process in March looks different than the process in May, and the process in May looks different than the process in August. The interesting question is, what is now the model that we would like to see? Would we like to see the model of the last month, of the last 2 months, of the last year, or forever? And this is related to the topic of concept drift. So the fact that we need to drop things from our memory can also be an advantage if we want the model to reflect recent behaviors. And there are all kinds of ways of handling this problem that kind of go outside of the scope of this course. But it shows the challenges that one is facing. To conclude, we look at a very concrete, also very simple streaming algorithm to compute k-means. And I'm going to repeat what k-means was. If this is not fresh anymore, please take again a look at the lecture dealing with that topic, and then we create a streaming variant of that, assuming that we have limited memory to do so. So this was the traditional non-streaming k-means algorithm. This is what I've explained in the lecture when we were talking about clustering. So what is the idea? We have multi-dimensional input data. So every circle corresponds to an instance, and an instance can have many features. In this example, only 2, but in reality it can be, I don't know, dozens of different features. And we try to find, let's say, structures in data. This is unsupervised learning that are reflecting, let's say, characteristic combinations. So if we, so in k-means, we decide the number of clusters up front. I've also explained techniques where that is not the case. This is just 2D, so this is a bit of a simplistic representation. So we have just 2 dimensions. We have just 3 clusters. And we initially just throw randomly 3 darts in this 2-dimensional space, and they are our initial centroids. Then we assign every instance to the centroid that is closest. So I was throwing these 3 darts, these 3 centroids, and all the instances that are closest to the green centroid are colored green. And so for example, this one is closer to the red centroid than it is to the green centroid. After coloring all the instances, we reposition the centroids by taking the average of the points that we have seen. So we go from this situation to this situation. And we repeat doing this. And so now this blue one is closest to the blue centroid. And so the blue, that's why this is colored blue. Then we reposition it, and now this blue instance is no longer closest to the blue centroid, it's closest to the red centroid. And we iterate until this stabilizes and does not change anymore. What we have seen is that we can reach multiple fixed points depending on our initialization. And so we often repeat this experiment a few times to come up with different clusterings, and we have a way of measuring the quality of such a cluster. I'm doing this at high speed because I've explained this in a previous lecture. But now you again know what clustering is, and specifically k-means clustering. But now we are looking at a situation where, so before, when I was doing, let's say, the repositioning of the centroids, I was keeping track of all the data. Like I was reasoning over all the instances that were in our data set. We are now looking at a setting where new instances are arriving every second, and we are accumulating data in such a way that we can no longer store all the data and continuously do a computation over all the data that we had seen before. So we want to do to bring this to the streaming setting. So the streaming k-means algorithm again tries to identify k clusters under the assumption that we cannot store all the instances, and we want to also deal with concept drift. So the cluster adapts to changes in the underlying process. So the assumption of this particular algorithm is that instances arrive in batches and are also processed in batch. So we process a batch and then the batch is forgotten. What I mean exactly by that will become clear in a few minutes. So the clusters reflect what we have seen in the last batch, but also in the batches that we have seen before. So it's a kind of moving average where, let's say, more recent observations are more important than observations that we made a long time ago. Okay, let's be a bit more technical. So we have k clusters. numbered 1 until k. For every cluster we have a centroid, CIT, and this is the centroid of cluster I at time t. So this is before the batch arriving at time t is actually arriving. If we look at this CTI, you should note that this is a vector. If you have 2 dimensions, this is a 2-dimensional vector, but in reality this is often a vector that can have, let's say, dozens of hundreds of dimensions. Then, so we have 1 centroid per cluster at a particular time t. So at time t, we have these centroids, and again, I'm repeating myself a bit, but just to be clear, is C1t is a vector. It is assigning a value to each feature for centroid 1, for cluster 1 at time t. And again, we have some strategy to start. And just like throwing the dart before, we can think of them as random initial centroids. What we now do is that we also assign a weight to the cluster. And that is because just like taking the weighted average, we have a kind of decay factor that is depending on the cluster. So the basic idea is that the cluster is more important if there are many instances in it. So next to the CTI, we also have a WTI, which is the weight of cluster I at point in time t. And so we have exactly the same representation, and these are the initial weights, and we could all give them the same weight. So what is now the main idea? And I will explain this, let's say, more technically in a minute. So we have a batch arrival. So in one batch, there is a new set of instances arriving. We assign each instance to the nearest cluster centroid, just as before. Then we update the cluster centroids and weights based on this batched arrival. It's basically applying, let's say, the k-means algorithm as we have seen it before. And we make the following choice, that if the weight of a cluster drops below a certain threshold, we kind of remove that cluster and create a new cluster based on splitting the largest cluster that we had so far. So clusters may disappear, and clusters that grow large can be split into smaller clusters. And so in terms of the naming, that if the old cluster J is split into new clusters, they're called I and J. And the cluster J, the old cluster J, then disappeared. Just to visualize this, so these are the clusters at time t. And every cluster has a centroid indicated by the black dot, and it has a weight which is indicated by the blue part. So the bigger the circle, the more important a particular cluster is. So every cluster has a vector describing the centroid, assigning a value to each of the features, and has a weight. And now we have a new batch arrival. So we are at time t, and at time t a batch bt arrives. And in red we see all the individual instances. What we do now is that we assign each of these instances to the nearest cluster, just like in traditional k-means. So for example, this instance is mapped onto this node, and we do that for all the instances that arrived in this batch. After that, we have every centroid has a bunch of new points associated to it, and we reposition the clusters. So the location is kind of an average of the old location and the locations of the new instances, and also the weight is updated. And of course, the more points are added to a particular centroid, the more important that cluster or that centroid gets. So it can be that by doing this process that there is a certain cluster that gets smaller and smaller and smaller relative to the others. Then we dissolve it if the weight drops under a threshold delta, and if we remove this old cluster I, we create a new cluster by splitting the biggest cluster into two parts, and one half of the cluster is taking over the role of cluster I that we had before. And so this is the situation before. We remove this cluster and we split this cluster into two new clusters. It is outside of the scope how this is exactly done. We are talking about the main principle here. So now I am able to describe more technically what it is doing. We have at any point in time for every cluster we have these centroids, which are vectors, and every centroid, every cluster has a certain weight, which kind of represents how important that it is, so how many instances went into it. Then we have a batch arrival at time t, and so at time t we have these centroids, these weights, and we have this batch arrival, and we split bt into several subsets in such a way that every subset is composed of the instances in bt based on their closest centroid. And so bt1 contains all the instances that arrived at time t that are closest to centroid c1t. b2t are all the instances, all the fresh instances that arrived in the batch and that are closest to centroid C2, etc. So BT is split into these K subsets. So every instance is now attached to one of the centroids. And then we compute the centroid of these newly arrived, let's say, sub-batches. So we partitioned the batch that arrived into K smaller batches, and we create a centroid for each of these new instances. So we are not considering the old instances. We already forgot about that. We can focus on the new instances that arrived in this batch. So we have a bunch of centroids based only on the new arrivals, and they also have a weight, and this weight is of course proportional to the number of instances in this batch. So what we see here is that the BC1T is a vector, is assigning a value to each of the features, just like C1T did. So this is a vector, this is a weight, the weight of this vector, and the weight of this vector is based on the number of elements in BT1. So the number of instances that we do. So BWTI is how many instances were in the batch that were assigned to centroid I, and BCT is the vector that is computed over all the instances in this particular part of the batch. And this is done as before, just as we were computing centroids in the classical k-means setting. So now we are all set, but now we need to assign a weight to the past and a weight to the new instances. And for that we use a decay factor. So if we have an alpha value close to 0, things that we have seen in the past are less important. If our alpha is closer to 1, then things that are, let's say, that happened in the past have a much bigger importance. We take the average of, let's say, the centroids that we have seen so far, plus the centroids based on the new batch arrival. So to be precise, we do alpha, so alpha is a value between 0 and 1, times WIT, that is the importance of cluster I at point T. CTI was the centroid of the cluster based on things that we have seen in the past. So what's in green is a vector. And we add that up. And so this whole thing is again a vector with a certain weight. Then we multiply that by the weight of the new arrived instances assigned to cluster I. This is the corresponding vector and the corresponding centroid just based on the things in the batch that were assigned to centroid I. And we divide that by alpha times WIT plus BW. So this is like a normalizing factor, because we multiply by that and then we divide by this. So what we can here clearly see is that if alpha is close to 0, then only the things that we have seen in the newly arrived batch matter. If alpha is close to 1, then we give a lot of weight to things that we have seen in the past. If we look at the weight of the cluster at time t plus 1, then that's alpha times the old weight with the decay factor plus the weight of, let's say, the instances that have been added. So if in the past we had a cluster that was based on very few instances, and then we have a batch and there are lots of instances assigned to this cluster, then the weight is increasing a lot. Conversely, if, for example, it could be that BWTI is equal to 0, then because we multiply this by alpha, then the weight is going down. If the weight of a cluster drops below a certain threshold, we remove that cluster and we split the largest cluster into 2 parts. And how that is done is outside of the scope of this lecture. So this is a visualization of how this works. So the black dots correspond to the centroids, and the color dots are corresponding to the instances. This is like it starts again and again. And if you look at the diagram that you see here on the left, is what you see is that there is a higher value of alpha. And so things that have been seen in the past are more important. So here we now suddenly see a change in data, and we see that the centroid responds slowly. And so it takes a while to adjust to the new, let's say, situation. If we look at the example that we see on the right-hand side, so let's again wait until it starts again looping. So now it starts. Now there is a sudden change in let's say, the distribution of the data, and there is an almost immediate response, because the most recent things are most important. So just in the extreme, this corresponds to a value of alpha close to 1. This corresponds to a value of alpha close to 0, and is adjusting faster. And we should, of course, mediate between these two, because choosing, let's say, a low value of alpha can also create a system which is very unstable, is very nervous. So even if it's in steady state. So we are looking for appropriate values of alpha in such a way that the centroids move smoothly with the data over time, as is indicated here. So as you can imagine, this is of course highly related to concept drift. If we have a high value of alpha, we are trying to compute something over a large time interval. If we have a small value of alpha, the most recent data is most important. So if we look at data over time, it could be that things are changing. So we are, for example, learning a decision tree in a particular situation, and then suddenly the underlying process is changing. Or we are trying to discover a process model, and the process model is steady for some time, and then suddenly there is a change. Then, using this alpha parameter that we just indicated, we are basically deciding what is the time period that we are interested in. So what kind of drifts are there? There can be a sudden drift. So there is a thing like Brexit or the COVID pandemic that is suddenly changing everything. It's something that it's very difficult to predict, but if you're using particular models, then of course your model should adapt to that new situation. There can be gradual shifts. So for example, like the economy is slowly recovering. That's a gradual drift where you can kind of predict what's going to happen next month. There can be seasonal drifts. I don't know, think of ice cream sales or certain types of insurance where you can see clearly a seasonal pattern. And there can be intermittent drifts that do not have a clear cause, for example, due to system failures. Related to our choice of parameter alpha is we should think, do we want our model to describe, let's say, long-term behavior or focus more on the recent behavior? So this concludes this lecture on big data technologies. So in this lecture we focused on the infrastructure part that is needed to deal with large amounts of data. Next to talking about infrastructures, there were two, let's say, very concrete things that we looked at. We looked at the MapReduce algorithm. You should know how that works, and you should be able to apply that to simple problems. And we looked at the streaming k-means problem. That's also something that you should be able to do yourself. Here is some literature that you can read if you're interested to learn more about these things. What is very important is that you prepare in time for the instruction. In the past, I would have multiple lectures devoted to the topic of big data, but I decided not to do that anymore because it's incredibly boring. You need to experience this, and many aspects of it are more engineering. I try to focus on the conceptual things. However, you need to apply this in your assignment. So you should make sure that you're able to install Hadoop and that you're able to code simple MapReduce algorithms on top of this infrastructure in such a way that you can experience this. As I mentioned in my lecture, I only spoke about the concepts. So that is the reason why there are two instructions devoted to big data. And again, I would like to stress, because you may encounter all kinds of technical problems, start this early enough. It's also something that you need for the assignment itself. Here we can see things that are in the reminder. There are still several instructions ahead. They are lagging a bit behind compared to the lecture, of course. There is one lecture left, and that is the closing lecture, in which I basically summarize what was in this course. I try to indicate what is important for the exam, and I also provide several pointers of, if you're interested in the field of data science, how you could further specialize in this topic.